Okay, OpenTelemetry with AWS. So, show of hands, who's heard of OpenTelemetry? Good. Probably half of you. Well, there's nothing for you here, so you can leave. More importantly, who uses OpenTelemetry? It's quite a lot less. These guys don't count, by the way. I work with them. So actually, maybe 5 people. So good. Hopefully, something for you. Ooh. So a little about me. I'm a senior cloud service engineer at YouView, where I've kind of been there 5 years. About 4 of those years using Go. The adoption for Go has kind of been growing ever since, and it's now our default language, which is great. The kind of mandatory social links, you'll be able to find the slides and the code that I'll share on the GitHub account there. This is kind of what I'm going to be covering today. So an introduction to what OpenTelemetry is, digging into OpenTelemetry tracing in particular. I'm going to talk about the collector and the role that it plays, and then we'll see how we use X-Ray to kind of visualize and export that telemetry data. So what is OpenTelemetry? OpenTelemetry is the mechanism by which code is instrumented to help make it observable. Kind of let's dig into that. What does that mean? Well, fundamentally, it's about observability. It's a set of tools and a specification and kind of supporting libraries that allow you to change the way your code functions so that you can observe how it is operating in a live environment. And that might be understanding how it kind of interacts with other services. More importantly, it's a standardization. So tracing isn't necessarily new. There's been lots of vendors that have kind of built their own specific solutions, and you depend on those vendor-specific libraries to kind of work and generate that telemetry data. Standardization is super important to be vendor agnostic because it promotes interoperability across your services, but also across the vendors that you can share data with. It's actually originates from a merger of Open Tracing and Open Sensor. So these were 2 separate things that kind of in the interest of having a single standard for kind of generating telemetry data and then defining its format and its structure resulted in the merger of those 2 and becoming OpenTelemetry in somewhere around May 2019. It's a cloud native computing foundation project currently in the incubating state. So it's definitely gaining a lot of traction. Instrumentation is supported in a whole bunch of languages, most importantly Go. But if you've got other services you kind of want to instrument, you can instrument those either manually for some languages, such as Go, or for languages like Java and others, there is auto instrumentation where you don't actually have to make changes to your code. You'll be able to run it through a tool that will manually kind of instrument code for you before you, or as you compile it or as you run it. So, digging into OpenTelemetry, the specifications kind of broken down into multiple distinct types of telemetry called signals. Each signal represents a kind of coherent standalone set of functionality. These 3 are often referred to, at least historically, as the kind of 3 pillars of observability. More recently, there's more. There's an article in particular that kind of talks about 6. But as far as OpenTelemetry is concerned, these are the 3 main ones. Each signal has a separate lifecycle and is managed independently. So it's versioned independently. The rate at which it becomes stable is independent. And kind of any changes are introduced independently. As we can see, traces has been stable for quite some time. The SDK has been around for quite some time, is very stable. Metrics, the API is stable, but the implementations are mixed. So in Go, for instance, there's been a recent kind of re-implementation to align it with the specification. So it's kind of mixed and it's very language specific. Logs is definitely not something you want to be using, but it's kind of being actively worked on right now. There is a 4th, it's called baggage. I'm not going to talk about baggage, but I'm just including it there for completeness. So let's look at tracing. So what is tracing and what is a trace? So a trace really is about capturing the sequence of events across all of the services for a given transaction. Now, a transaction might just be a HTTP request. It might be an event or something that's kind of propagating through the system. But inside a trace, it's comprised of 1 or more spans. And then a span represents the unit of work or operation. It includes time-sensitive information like when it started, when it ended, and also attributes. It might be things like what was the HTTP method, what was the URL that you're hitting. You can include custom attributes as well, such as what was the ID of this thing that was coming in, what's the user name, whatever it might be. You can associate that with those individual operations. It's kind of similar to logs. So you can see this is a JSON representation of that. It might be quite hard to see at the back. But you've got a trace ID, a parent ID, span ID. These are very structured and formalized key value pairs. So a lot of the names are part of the semantic convention of OpenTelemetry. If we visualize that, this is an example of a trace kind of represented as a flame graph. This is the entirety of a trace, and each kind of block, each bar on this is actually a span. And there's an important one here, which is the very first span, part of the trace. And that is called the root span. And the root span is responsible for generating the trace ID, which all other child spans are kind of linked to. The way that the kind of relationship works is, other than the root span, every child span has a link to its parent, and it also has a link to the broader trace ID, which is how it kind of groups everything together. So why should you trace? Ultimately, it helps to provide end-to-end visibility into how your distributed systems are behaving. Quite crucially, and particularly kind of go back to that first talk, it helps you understand what your service dependencies are and also the relationships with those things. So what services do my service talk to? How many times does it talk to those services? What's the latency there? What's the average failure rate? All of those things you can kind of capture in the telemetry and visualize later on. Specifically talking there about performance bottlenecks, each span has can be, because it has that time capture information, you can see how long it took, what was the latency there, and you can kind of identify individual traces that stand out from others and kind of use that telemetry to derive insight. Very importantly, though, it allows teams to speak the same language. So typically, in a distributed system, different teams look after different parts of the system, and what each team is able to do is be given a trace and say, look, we know there's a problem in this part of the system. We know that you look after that. Here's a trace that includes exactly how to kind of reproduce it, all of the inputs that were coming through the system. And it's a common set of definitions, that a language that a team can communicate with. Tracing isn't free, though. There's some considerations that you have to consider. First of all, it's kind of the overhead. So tracing introduces changes in your code in the sense that there is kind of minor CPU and memory overhead to this. So you're capturing data as the system is running. You're potentially processing that or sending it somewhere else. That's not free. Minor latency increases as well. Again, we're talking nanoseconds, but it depends on how much you use it. Because as your service is doing extra work, it's going to take more time. There's an overhead potentially for migrating away from a vendor-specific solution. So you may want to kind of come off of a vendor-specific and become and adopt OpenTelemetry, which is something that we did. And then cost. So there's the cost of running your backend, or paying a backend provider to kind of host and aggregate that telemetry data that you're generating. Cost in engineer effort to manually instrument or to migrate away. That takes time. So yeah, not free, but the benefits definitely outweigh the costs. But to reduce costs, there is something you can do with trace sampling. So sampling is the process that restricts the amount of trace data that is generated by a system. If systems are kind of operating normally, then there's not a lot of useful information that's generated by a trace. What might be useful is when something goes wrong, because at least then you can kind of dig in and understand why that went wrong. Trace sampling is a mechanism to reduce the overall volume of telemetry and instead focus on things that might be important. So where to sample? You can do it as head-based, which tends to be the kind of default approach. And that would be where a request comes into your system. And at that point in time, you make a decision as to whether this trace is going to be sampled. And therefore, everything that follows it potentially will be sampled as well. And then that data is exported down the line. Or you may do it tail-based. So at the end, once all the telemetry data has been collected for that service or a set of services, you might decide, was there anything interesting about that trace? Is it worth actually then exporting it on? So you can opt to sample it at the tail end of the call as well. So that's where, and then you have when. So when should the sampler decide to sample? So the default is always on, sample everything. Why not? Let's generate all the data. Parent-based is an alternative, and that says, when I decide whether this span should be sampled, I'll look to see what the parent is doing. If the parent is sampled, I will be sampled. If it's not, then I won't either. So that kind of has an effect, where if the first thing isn't sampled, nothing else below it would be. Trace ID ratio based, so that's just a kind of way of reducing the, or randomly picking a trace to be sampled based on a kind of ratio or percentage. So you might do 1 in 10 spans, 1 in 1,000 spans. Or finally, remote-based, which is where you're sampling dynamically based on a remote rule set. So your service would communicate with some external configuration and say, what's the rules in which I should sample, and it will then use those rules to decide whether it should sample. And those rules can change in live without making any code changes. One of the other things here is, obviously, as you reduce the rate of sampling, you reduce the visibility into your system. So head-based, tail-based is an important decision to make. So let's have a look at some code to set OpenTelemetry up. Can you see that okay? See some nods, good. So this is a very basic, kind of very minimal Go service. And we're going to look at how we initialize OpenTelemetry to make it function properly within our service code. So these are there's a couple of components here that we have to initialize in order to kind of operate correctly. And the first thing that we want to do is create a resource. Now, resource is responsible for defining your service individually as a kind of node in the wider system. And how that looks is you kind of assign keys to a resource, such as the service names, inventively, service A. You can attach things like the version of the service, some custom key value pairs, whatever you want to do, but that kind of helps describe your service within the broader system. So that's the resource. You define an exporter. The exporter is responsible for kind of considering where to emit the telemetry data. So it's great if you generate the data, but if you're not sending it somewhere or printing it to the console or doing something with it, then it's no good. So in this example, we are creating an OTLP exporter, or the OpenTelemetry protocol exporter, and we are sending the data to the OpenTelemetry collector, which I'll talk about shortly. But we're taking the data that we generate by the service and we're passing it on to the collector to kind of manage that for us. So we have the exporter, then we have the sampler. So I mentioned the sampler is responsible for deciding what to do, when to sample a span or a trace. Some examples here, we've got never sample, which I don't even know what's an option, it defeats the point. Always sample, trace ID ratio based, or actually something here called parent based, which I said it looks at what the parent is doing. But then more importantly, if there is no parent, because it's the root span, you can provide a separate configuration there. So we always sample in this case. And I believe this is the kind of approach that is recommended by the OpenTelemetry docs. So see what the parent is doing, and in the case it's the root, always sample. So once we have those three resources, we can then create a trace provider. And a trace provider is just a factory. It's a factory for creating traces, which are the things that you can then start and stop to create your spans. An interesting note here is because we're working with AWS X-Ray, we have to use their own ID generator. So they are not W3C compliant with the trace IDs that they use. They actually encode timestamp information in the 16 bytes that they generate for their ID. And because of that, there is extra meaning inside of it. So we have to use the X-ray generator to generate the ID, which then AWS will accept. So that's why we have to provide an ID generator. It's just an interface, so you can have other things that might generate IDs differently. Oops. I'm so glad that I had that, thanks. If your camera's dead, put it down. Oh, right, okay. Okay, moving on. So that's the trace provider. Importantly, we've created things that are contained within the SDK. We have to register this trace provider on the OpenTelemetry API, and that's so other instrumentation libraries can retrieve a trace provider. So it's the way of decoupling instrumentation libraries that use the API from the specific implementation of the SDK. Additionally, as well, we have to set a text map propagator. So this is to do with trace propagation across API boundaries. In our case, we need the X-ray propagator again. So that takes tracing information out of the active trace. In our case, it would serialize that into a header, which hopefully you can see just above the line. And that's a very bespoke format to X-ray. So it is responsible for generating that format, inserting it into a header, which is then recognized by other downstream services or AWS services specifically. And that's kind of it. It seems like a lot, there's a lot of boilerplate there, so it's kind of useful to wrap that up into a library or a module of your own, and then other services can just call that. We also have a HTTP server that we set up for the purposes of this demo, and we're using Mux, which hopefully most of you have heard of. Now, Mux by default is not instrumented with AWS, with OpenTelemetry. It doesn't have native integration with it. So in order to kind of make it so that it can create the span information, create the traces, we have to defer to a contrib library, which is providing Gorilla Mux OpenTelemetry support. And what that does is it injects the middleware right at the beginning. So one of the first things that your request will be routed through is the OpenTelemetry middleware for Mux. It will create spans, register the calls, and extract the HTTP status and other useful information back out again. The rest of it is fairly standard boilerplate, and I will show this running a bit later. Switching back. Cool. So the collector. I kind of talked about the services responsible, or at least we've configured the service so that it's generating telemetry data, but it's sending it out to the collector. So what's the collector? Architecturally, it kind of sits separately from the services that are sending data to it. And it's in the middle between services generating telemetry and the exporter backends that you want to send telemetry data to, so you can kind of visualize it or analyze it outside. But it's a vendor agnostic way to receive, process, export telemetry data. Typically, this runs as kind of a local collector agent, so it might run as a sidecar or as a separate pod or something as part of your services, but you can run it in multiple configurations. We're kind of zooming in and looking inside the collector is comprised of three major components. So the receivers on the left define the inbound format of data. What is the telemetry data that we're allowing the collector to receive? Define the port to receive data. So in our case, you've got the OpenTelemetry protocol, OTLP, but you might also, your services might be instrumented to generate Jaeger, Prometheus, or maybe even older open census data. And the collector can receive that data. So you might just want to take your local agents that are running for those vendor-specific providers and provide the collector and run that instead, kind of drop in replacement, and then it can be responsible receiving those vendor-specific formats as well. You can then define processors, which are responsible for kind of filtering or processing your data, doing some sort of transformational job. You may want to filter out certain events. You might want to introduce the TEL-based sampler that I talked about, so we can decide at this point in time whether that trace is of any use, or there's no errors, it's potentially not a useful trace, doesn't provide any insight. And finally, batching. So you want to batch up the data that you send as well to kind of reduce network overhead. And then finally, you've got the exporters. So where do I want to send this data? So you can send it to Jaeger, Kafka, Prometheus, X-Ray. There's a whole bunch of them supported out of the box. There is also collectors that have been wrapped and provided by vendors as well, which I'll talk about later, which is how you can extend what exporters and what receivers are provided. So why use the collector? Well, quite simply, it allows you to offload telemetry data quickly, make it the responsibility of the collector to manage, process, handle authentication, retry logic, batching, encryption, etc. So each service, it doesn't have to know how to do that, doesn't have to take that responsibility. Avoid managing multiple vendor-specific agents. You don't need one for each vendor that you're working with. You just have one collector that can be configured to work with all of the telemetry data formats that you may want to use. It's configurable. You can easily add a new backend just by reconfiguring the collector. You don't need to make service changes anymore. Suddenly, you could be trialing out a new exporter backend, a new provider, and you want to send data to them as well as the one that you're currently using for evaluation. Just reconfigure it, add a new exporter. And then similarly, it's very flexible and extensible in the data processing. So you can add your own custom processors. You can use ones that have already been built to kind of conditionally decide what to do with trace data and kind of enhance it that way if you want to. Deployment strategies. So I mentioned a sidecar approach. This idea that you've got kind of Docker compose one container that's matched with another, and they're attached together. So service A is always sending data to its version of a collector that's running. Service B has got its own version of the collector running, and it's sending data to that as well. So that tends to be quite a nice, easy way to run the collector. That might be in your container orchestrator of choice. Alternatively, is a daemon, so it's running directly on the host, not inside a container, and then your Docker containers that are inside an orchestrator might be sending data to the local host to process as well. Interestingly, in this setup, the collector can also collect telemetry data about the host itself. So it can collect how much CPU is in use, how much memory is available. It can collect more information from StatsD and various other sources that can help enhance how you can visualize your traces. So a particular trace might be bad because the host was bad, but you can kind of potentially correlate that data later on. Alternatively, there's a gateway. Now, I haven't really found a use for this, but one thing someone else mentioned to me was that actually it can be quite useful if you've got security policies in place where you say the host on the left where your services cannot talk to the outside world. It's very constrained. Network access is limited. So instead, you send data to another host which has the right security groups. It can allow outbound traffic. And then you can kind of deploy a whole set of collectors which are load balanced. It does introduce complexity because if you need to load balance those, sometimes you might want to load balance based on trace ID so that the same tracing information goes to the same instance, which allows you to do tail-based sampling. It kind of gets a little bit more complicated. Distributions. So I said earlier that there are providers out there that wrap the OpenTelemetry and provide their own version of it. It's just kind of building it with some custom setup, and you can then add your own custom exporters, your own custom receivers, possibly even custom processors. And OpenTelemetry provide a tool for this. It's called the OpenTelemetry Collector Builder. And that will generate a binary for you based on your config and your references to particular exporters. Most importantly, the one we're using is the one provided by AWS, which they call their ADOT collector, which hopefully visually you can see it's very much the same sort of thing, but I've just highlighted that they provide exporters directly to X-Ray, and then the EMF, or embedded metric format, I think it stands for sending metric data to CloudWatch. And then on the receiver side, they support OTLP, which comes by default, and they also support receiving X-Ray data. So originally we've got services that are directly tied to X-Ray as a vendor, so we're using the X-Ray SDK. We can send data straight to the collector without needing to change service code. We just kind of drop in the collector it'll listen on the same port, and we can export it to the same place. So it's kind of phasing out vendor-specific implementations. So X-Ray. Let's demo it. Rather than talk about it, let's try and demo it. What could go wrong? Thanks. So, on the left, I have 3 services. Let's assume we don't know how they work together. It's kind of obvious A, B, and C, but let's assume we don't. I'm going to, this is cutting off for some reason. I'm going to run them with Docker. Now, if we just look at what I've run, so in Docker Compose, I will make this smaller a second. We have service A, service B, service C, and separately we're running the collector locally. So I've got 4 containers, some of which can talk to each other. And the collector is running separately, and all 3 of them are sending data to the same collector. Now, in this scenario, I have printed out a URL to localhost, which when I hit, we've got a random basket ID. It's not super relevant, but I'll show you where that appears later on. Now, the trace ID that's generated, this is kind of an interesting thing here. So the trace ID that's generated by the X-Ray ID generator looks like this, which looks like the W3C format. It's the format that OpenTelemetry is expecting to see. Underneath it, for convenience, I've actually formatted it as X-Ray would expect to see it. Now, this normally happens in the collector, in the X-Ray exporter. It will see this data and it will transform it just as it's prepping to send that data to AWS X-Ray. But for convenience, I've kind of put it here so I can copy it and we can discover the trace. If I go to X-Ray, make this a bit bigger. This is not This is falling behind. It's still falling behind. Just wait a second. Okay, I'll make it. Did say what could go wrong. Apparently the network. If I go to CloudWatch. Yeah, it's not loading for me here either. Let's give it a minute. How am I doing for time? Nervous, but thanks. Yours? Yeah. Stop sharing again. Well, it's just loaded for me, so.
Yeah, it was working until now, and then like now it's like.
Yeah, now when it matters, it doesn't work. Yeah, I've got a few more pages to load first. Okay, so that's the service map. This might be quite hard to view. Might need to zoom out slightly. Here's the trace I just generated. But we're looking at a view that's showing all of the traces that have just come in the last 5 minutes. I only generated one, so conveniently it's here for us. But what I can do, if I was interested in a particular issue, I could click on service A, that's the service I look after, and I can say view traces. Let's get rid of this because it puts the wrong information in there for the demo. You can see there was one trace which matches the transaction that I demonstrated. We'll look at that trace specifically. And I think the network issue has ruined the demo because there should be some errors that we're going to look at, but we might not have the whole telemetry data yet. So one of the parts of the problem is each service is generating telemetry data and it's sending it to the collector. The collector is processing it, sending it to AWS. But somewhere along the line, we've got a lot of latency and it's not doing that job. But we can see a picture. Let's see, that's visually how we can kind of understand that service A is talking to service B. Service B is sending a message to an SQS queue, which is then being read by service C. Service C is talking to Dynamo, it's talking to S3, and it's making, which will see several requests to HTTP stack to us. So very quickly, we can see exactly what, not just our service, but what other services are doing. So we can understand the dependency of our services. I want to scroll down. Okay, there is errors, it's just that the thing hasn't updated. But we can look into that more in more depth. So I mentioned this flame graph kind of view, which allows us to go into more detail. So we can see service A, this matches the HTTP request that I made in the browser with our ID. I've got a custom span in the service, which I've labeled make payment. And if we look at the metadata associated with that, I've attached some custom attributes. So a transaction ID, which could be useful if you needed to extract more information out. The basket ID as it came in on the HTTP request. It then makes a post request to service B. And we can see the URL that was used there and the transaction information that's on the query string. Service B processes a payment. Of course, it's not really doing that, but that took 2 seconds. It sends the message to SQS. Because of the latency, it took 3.4 seconds to do. Blame the network. But you know, this is real life, right? We get network latency all the time. So that went through SQS and then was received by service C. Service C made a put item call to Dynamo. And we can see that the table name that was used was Luke's Hotel Demo Table. We can see that then we made a couple of requests. These two here, so HTTPS and S3, these two bars overlap, and that's because they were done, the operations were concurrent. They were happening at the same time. And then there's a couple more requests. Actually, 2 of these should not be 5xx, and that's because we genuinely had a network issue. And you can see the latency there. So it was supposed to demo what a 4xx looks like, and then what one deliberate 5xx was going to look like. For instance, this is supposed to return, so if I can zoom in, a 404. Didn't happen. It's because the request actually failed. So yeah, a 5xx in our case, we can, let's see, I think it might have resulted in an exception. Yeah, it did. And this is the exception. So it's TLS handshake timeout. So we can see that the actual error information gets attached to the span. So in our case, we can prove that actually, yeah, it was, the network's terrible. So yeah, that's basically that demo, I think. And then what happens as well is it groups it at the bottom based on the kind of call to the particular resource. So for instance, we can see the individual calls to the HTTP stats nicely grouped and not necessarily in the chronological order as they occurred, the call to Dynamo and call to S3. So yeah, that's how you can kind of visualize that trace and understand the dependencies. Let's go back to this. Okay. To wrap up, here's some resources if you want to kind of learn a bit more. So my slides and the code, if you want to kind of dig in to see how that's working. OpenTelemetry docs, the contrib libraries, ADOT, so Amazon's own wrapper around the collector. This is a very useful book as well at the bottom. So the future observability from Lightstep by Ted Young, useful resource. See somebody taking a picture. So. Okay, good. And then most importantly, it's Trend. If you want to get involved, we're hiring. Come talk to me, scan that. But yeah, that's it. Questions? Sorry, 30 minutes. Blame the network. It's not my fault. Come and talk to me after.
Right.
Oh, one now. All right, one.
So I was going to ask about, which I think I now know the answer. It seems very synchronous and HTTP specific, but it seems like you were doing tracing over a queue as well.
Yes.
So asynchronous support is, I'm going to call it kind of out of the box, something you can do. Which...
It is out of the box, kind of. So last week it wasn't working with AWS. Fortunately, I contributed something that made it work, which I needed for this demo. So that's great. So you can now, because of that context propagation where you insert headers into how the AWS SDK is working, it's sending trace information to SQS. SQS can then attach that to the message. And then when service C is reading it, you do have to manually extract tracing and inject it into the context to continue that trace. Otherwise, like batching operations are kind of independent, but the message is, the processing of that individual message is specific to where it came from.
And is that SQS specific? Or because there's obviously other eventing mechanisms, which would be good if it worked.
Yes, we generally use SQS, but there's various, look at the Go contrib and you'll find instrumentation libraries that can add it to other queue mechanisms. But yeah, as long as you can propagate tracing through a queue, if it supports it, or you can attach it to the individual message itself, then yeah, it's possible. Cool. Thanks.
Thank you very much.